Hi class, how are you today? That's probably great. Chapter 4, Elementary Probability Theory. The learning target for today is to be able to calculate and understand probabilities. Number 3, you are a 3 on the scale if you can calculate and understand probabilities. 2, you can calculate or understand probabilities. 1, you can state the sample space of a problem. Or 0, you do not understand probabilities. Let's get started. Section 4.1, what is probability? Focus points for this lesson. Assign probabilities to events. Explain how the law of large numbers relates to relative frequencies. Apply basic rules of probability in everyday life, and explain the relationship between statistics and probability. When we use probability in a statement, we're using a number between 0 and 1 to indicate the likelihood of an event. Probability is a numerical measure between 0 and 1 that describes the likelihood that an event will occur. Probabilities closer to 1 indicate that an event is more likely to occur. Probabilities closer to 0 indicate that the event is less likely to occur. P of A denotes the probability of event A. If P of A equals 1, event A is certain to occur. If P of A equals 0, event A is certain not to occur. So it's essentially 1 and 0 are 100%, 0%. So if you get a probability of A being 0.85, that's 85% chance that event A is going to happen. Probability assignments. A probability assignment based on intuition incorporates past experience, judgment, or opinion to estimate the likelihood of an event. This is, of course, the least trustworthy, the least useful, but people still use it. So it is a type of probability. A probability assignment based on relative frequency uses the formula probability of event equals relative frequency equals F over N. You'll remember this back to histograms. So another way we use relative frequency is to figure out the probability of an event. Where F is the frequency of the event, occurrence in a sample of N observations. So F is how many times the event occurs in however number you have. Number 3, a probability assignment based on equally likely outcomes uses the formula probability of event equals number of outcomes favorable to event divided by the total number of outcomes. Consider each of the following events and determine how the probability is assigned. A sports announcer claims that Sheila has a 90% chance of breaking the world record in the 100-yard dash. It is likely the sports announcer is using intuition based on Sheila's past performance. So just going with intuition, no hard facts or anything, just that's what the sports announcer thinks. There may be some facts that he's using, but it's pretty much in his head, and he could explain his reasoning, but it's not mathematically proven. Henry figures that if he guesses on a true-false question, the probability of getting it right is 0.5. In this case, there are two possible outcomes. Henry's answer is either correct or incorrect. Since Henry is guessing, we assume the outcomes are equally likely. There are n equals 2 equally likely outcomes, true or false. And only one is correct. So by the formula P of correct answer, so probability of getting the correct answer, is the number of favorable outcomes, 1, divided by the total number of outcomes, 2. 1 over 2 is 0.5. C. The Right to Health lobby claims that the probability of getting an erroneous medical laboratory report is 0.4. Based on a random sample of 200 laboratory reports, of which 80 were erroneous. So, the way they found it was the formula for relative frequency gives the probability with sample size n equals 200 and number of errors f equals 80. So the probability that there's an error is relative frequency, f over n. So 80 number of erroneous reports divided by the 200 total reports. 80 divided by 200 is 0.4. The technique of using the relative frequency of an event as the probability of that event is a common way of assigning probabilities and will be used a great deal in later chapters. The underlying assumption we make is that if events occurred a certain percentage of times in the past, they will occur about the same percentage of times in the future. In fact, this assumption can be strengthened to a very general statement called the law of large numbers. In the long run, as the sample size increases and increases, the relative frequencies of outcomes get closer and closer to the theoretical or actual probability value. The law of large numbers is the reason businesses such as health insurance, automobile insurance, and gambling casinos can exist and make a profit. No matter how we compute probabilities, it is useful to know what outcomes are possible in a given setting. So for example, say you flip a coin 10 times. As you know, you'll have a 0.5, 50% chance of getting heads or tail each time you flip. But if you flip it 10 times, it might not necessarily come out to a 50-50 split. It might be more like 6 or 4 or 7 or 3. So it'll lean closer to one side, but if you do 100 times, you'll get it closer to being a 50-50 split. And if you do it 1,000 times, you'll get even closer to a 50-50 split. So the more times you flip that coin, the closer and closer it'll get to actually being 50% heads, 50% tails. For instance, if you're going to decide the probability that Hardscrabble will win the Kentucky Derby, you need to know which other horses will be running. To determine the possible outcomes for a given setting, we need to define a statistical experiment. A statistical experiment, or statistical observation, can be thought of as any random activity that results in a definite outcome. An event is a collection of one or more outcomes of a statistical experiment or observation. A simple event is one particular outcome of a statistical experiment. The set of all simple events constitutes the sample space of an experiment. So a simple event is one thing happens, such as you flip a coin and it becomes tails. The sample space is all the possible things that could happen. So you flip a coin and you get heads or tails. That's the sample space. But if you say flip 2 coins, a simple event would be that you get tails twice. But the sample space would be getting heads twice, getting heads then tails, getting tails then heads, or getting both tails. So in that case, the sample space is much bigger. Here's another example of it. Human eye color is controlled by a single pair of genes, one from the father and one from the mother, called a genotype. You may have learned about this in biology. Brown eye color, B, is dominant over blue eye color. Therefore, in genotype, brown-blue, consisting of one brown gene and one blue gene, the brown gene dominates. A person with a brown-blue genotype has brown eyes. So you'd need 2 blues in order to get blue eyes, but any other gives you brown eyes. If both parents have brown eyes and have a genotype brown-blue, what is the probability that their child will have blue eyes? What is the probability that their child will have brown eyes? To answer these questions, we need to look at the sample space of all possible eye color genotypes for the child. They are given in Table 4.1. So if you look at this table, it's possible of getting a brown from the father and the mother, possible of getting a brown from the father and a blue from the mother, or getting a blue from the father and a brown from the mother, or getting a blue from the father and a blue from the mother. That's the sample space. These 4 different events make up the sample space. And the one we're looking for is the event that we get blue eyes, which is 2 blues. According to genetics theory, the 4 possible genotypes for the child are equally likely. Therefore, we can use the formula to compute probabilities. Blue eyes can occur only with the blue-blue genotype, so there is only one outcome favorable to blue eyes. So the formula is the probability you have blue eyes, number of favorable outcomes, divided by the total number of outcomes. As we saw in the table, only one of those, this one here, will give blue eyes, and there's 4 total. So 1 over 4, or 0.25. Brown eyes occur with the 3 remaining genotypes, brown-brown, brown-blue, and blue-brown. So the probability that brown eyes happens is 3 over 4, because you have 3 chances of getting brown eyes out of 4 possible chances, so a 0.75 probability. The sum of the probabilities of all simple events in a sample space must equal 1. We can use this fact to determine the probability that an event will not occur. For instance, if you think the probability is 0.65 that you will win a tennis match, you assume the probability is 0.35 that your opponent will win. The complement of an event A is the event that A does not occur. So we use the notation AC to designate the complement of event A. Notice that the 2 distinct events A and AC make up the entire sample space. Therefore, the sum of their probabilities is 1. So in this case, probability that you had blue eyes was 1/4. The probability that you didn't have blue eyes was 3/4. 1/4 plus 3/4 is 1. The complement of event A is the event that A does not occur. AC designates the complement of event A. Furthermore, the probability of A plus the probability of the complement of A equals 1. So the probability that event A does not occur is the probability of the complement of A. And to find that, you can just do 1 minus the probability of A. The probability that a college student who has not received a flu shot will get the flu is 0.45. What is the probability that a college student will not get the flu if the student has not had the flu shot? So in this case, we have the probability of getting the flu is 0.45, so the probability you will not get the flu is 1 minus that. So 1 minus 0.45 is 0.55. Probability related to statistics. We conclude this section with a few comments on the nature of statistics versus probability. Although statistics and probability are closely related fields of mathematics, they are nevertheless separate fields. It can be said that probability is the medium through which statistical work is done. In fact, if it were not for probability theory, inferential statistics would not be possible. So we use probability theory in order to make inferences to say things about statistics. So we need probability theory in order to make sense of stats. Put very briefly, probability is the field of study that makes statements about what will occur when samples are drawn from a known population. Statistics is the field of study that describes how samples are to be obtained and how inferences are to be made about unknown populations. A simple but effective illustration of the difference between these two subjects can be made by considering how we treat the following examples. Example of a probability of application. We know the exact makeup of the entire population. So we say given 3 marbles, 5 red marbles, 4 white marbles, in a bag draw 6 marbles, random from the bag. What's the probability that none of the marbles is red? So we're not going to do that right now, but that's probability. Statistical application of it. We have only samples from an otherwise unknown population. Draw a random sample of 6 marbles from the unknown population of all marbles in the bag and observe the colors. Based on the sample results, make a conjecture about the colors and numbers of marbles in the entire population of marbles in the bag. So we're using the probability, the kind of thing we did in the first example, to help us with the second example of what do the marbles in the bag look like. Now time for the sponge activity. Just a short one today. On a 3-question true or false quiz, first, what is the sample space? And then, what is the probability of having all the questions be true? All right, that's it for this lesson. Once again, please make sure to take notes in the entire lesson. Don't forget to rank yourself on the scale and put it so where I can see it, probably at the top of your notes. Don't forget to attempt this sponge, and yeah, actually do the videos. Yeah, that's good too. Have a good night.